look at practice question set number 15 here, everyone. It says, use the following information to answer the next two questions for question 1 and 2. XY represents a section of a current carrying wire, and it does tell us in bold that it's conventional current. We don't see that very often, but occasionally we do. Okay, this is purposely put up there just to expose you to it. If we see conventional current, we know that that means the flow of what? It means the flow of positive. So that means if we're going to use a hand rule, it's going to be a right-hand rule. If I ever see those words, I'm going to just abbreviate right-hand rule with RH just to remind me when I go to do the hand rule that it is a right-hand rule. Now, if I don't have to do a hand rule for this, oh well, I wrote down RH for nothing. No big deal. Okay, I wasted 0.1 milliliters of ink. It's probably not going to be a big deal. Now, we also given an equation for the magnetic field at any point around the wire. Now, that's an equation that we don't recognize. We've never seen that before. We'll probably never see it again. It's not one that's required for Physics 30. That's why they give it to us in this question, as opposed to expect you to go to your data sheet for that. It says mu, which is just a constant, times I, which it tells us is the current in conductor Y, XY, 2 pi times R. R is the distance from the wire. One thing that's kind of interesting here, not that you need to know this, but one thing that's interesting is that the magnetic field is inversely proportional to the distance versus inversely proportional to the distance squared, right? With the electric field and with gravitational field, we see those fields inversely proportional to the distance squared. We see it inversely proportional to the distance here. Question number 1, we want to find the direction of the magnetic field produced by the current in XY. We've learned 2 hand rules so far, and clearly we're going to use one of them to solve this, right? We've learned the wire grasp rule, which is thumb, current, fingers, field, and we've learned the coil rule, which is fingers, current, thumb, field. Which one are we going to use here? It's the wire grasp rule, right? We don't even have a coil. So how are we going to use the coil rule for this? It's just going to be a wire grasp rule. And it's going to be a right-hand wire grasp rule because it's conventional current. So we're going to take our right hand. Everybody take your right hand now. Stick your thumb, your right thumb, in the direction of the moving charge, which is from X to Y. Now, we're going to make sure that our fingers are above the wire here. If the current is going this way, if you have a look up here, at the ruler with the arrow on it. If the current is going this way, we want to make sure, and the point P is above the wire, we want to make sure our fingers are above the wire. Not like our knuckles, not like whatever other part of our fingers, but our fingertips, our fingernails are above the wire. Which way are my fingertips pointing right now if they're above the wire? Which way is it? Out of the page. So the answer for this is out of the page. Now, some people might get confused because you see a dot here. Oh, it has to be out of the page because there's a dot. That dot isn't meaning direction, right? That dot is just showing a place. We want to find the field strength at that spot. It happens to be a dot, and we would represent that direction by a dot, but that's just a coincidence. Okay, they're not trying to tell us with that it's out of the page. Now, question 2 says, if the current in the conductor XY is doubled and all other variables remain constant, what's the magnetic field strength going to be at point P? This is really a variable value changing question, but it's one that we can probably do in our head, right? If we're changing the strength of the current to twice the current, then what effect is that going to have on the magnetic field? Just double it. It's just going to double it, right? So the magnetic field strength is going to be just, where is it? C. It's going to double the strength of the magnetic field. And 3, the north pole of a solenoid. What's a solenoid again? It's a coil of wire, yeah, and clearly we have a coil of wire there, a solenoid. It's showing up position 1, 2, 3, or 4. What hand rule of the 2 that we've learned so far are we going to use for this? The wire grasp rule or the coil rule? Coil rule. Now, you can actually make the wire grasp rule work here. It's just not easy to make the wire grasp rule work here. So we're going to use the coil rule. We know right away the answer is not going to be what? It's not going to be 2 and 4. Okay, it's going to be either 1 or 3. Let's figure out which one it is. We got a battery here. The battery, do you want to use electron current or conventional current? Probably electron current because that's the way that it really flows, right? I'll use the electron current here. We're going to say this is the positive terminal of the battery, this is negative. If we're using electron current, it's going this way, down in the front and then up around in the back, right? All right, everybody take your coil out that you made yesterday. If you don't have it, then roll up another piece of paper or use your water bottle or something. Got a quiz on this stuff on Monday. Bring this in on Monday. That's fine. Or if you forget it or lose it, whatever, make another one. That's fine. You know what I just thought of? As I just saw somebody putting hand cream on and doing this a little bit. If you don't have that coil, your arm can be the coil, right? Literally, your other arm can be the coil. So we can say, we just have to make sure that you write the word front on your arm, right? We'd say, fingers in the direction of the magnetic field. Fingertips on the word front. So fingers in the direction of the current, right? Fingers on the word front, pointing downward in the front. Why? Because you can see clearly here that these arrows in the front of this coil are pointing downward. So fingertips on the word front, pointing downward, just like we have on the board there. Thumb's going to point automatically which way? To the left, to the left. So thumb's going to point to the left, means the magnetic field is this way. If the magnetic field is this way, what's this going to be? Number 3. That's going to be south, this is going to be, didn't we say the magnetic field goes from north to south? Not inside, outside it goes from north to south, inside it goes from south to north. So my answer for this one is 1. And 4, if the current carrying wire runs directly over a magnetic compass, the needle of the compass will point which way? Let's say that this is the wire. Okay, this is the wire. We put a compass, let's do the wire like this actually, horizontal like this. We put a compass right below it or right above it. It doesn't really matter. Compasses are supposed to point in the direction of a magnetic field, right? So which way is the compass going to point? Well, we don't really know whether it's into the page or out of the page. Depends on which way the current is going, right? But we do know that the magnetic field will be what? Yep, Parker? Yeah, it's going to be perpendicular. We can do our hand rule to figure that out for sure, right? Let's assume the current is going this way. My thumb is going this way. Fingers right above are going into the page. Right below, they're coming out of the page. Either case, it's perpendicular, right? So if the magnetic field is perpendicular here or here, then the compass would point perpendicular to the moving charges as well. You guys probably don't remember this because it wouldn't have struck you as meaningful when we did this. But the day that we introduced the first rule, which is the wire grasp rule, we introduced it with that treasure map. Remember, with the treasure map, and we had a wire underneath the treasure map with an electric current flowing through it. And I don't know if you remember this, but when the current was going through that wire, we said that the compass needle pointed in a different direction. Do you remember which direction I said it pointed? And you may have thought that when I did that, it was random. It wasn't. I purposely made the wire go up and the magnetic field go perpendicular to that because that's the way it is. It wouldn't have struck you as being wrong when I did that because you didn't know any better, but I still didn't want to be wrong. The magnetic field is always perpendicular to the wire. Therefore, the compass needle would point perpendicular to the wire. Make sense? So which one is it? A would be. And number 5, an automobile's battery delivers steady DC current to a headlight. DC just means direct current. We use direct current comes from batteries, solar cells. Okay. Alternating current is used in our houses. Direct current is current that goes in one direction and maintains a constant value. It's not changing back and forth. Alternating current is current that's going this way, and then it's going this way, and then it's going this way, and then it's going this way. It changes direction 60 times per second. We use alternating current in our houses for one reason and one reason only. It's cheaper to transmit on power lines than direct current is. It's a cost thing. It's cheaper to transmit because we have less power loss over the power lines with AC current than we do DC current. That's the only reason we use alternating current going back and forth. DC current, we don't have to transmit it over long distances in your car. We use DC current. Now, what does the electric current, this DC current, produce? Is it going to produce an electric field? Yes. Is it a circular electric field? No. Does it produce a magnetic field? Yes. Is it a circular magnetic field? Yeah. The magnetic field surrounding a current-carrying wire is going to be circular. A gravitational field, it does produce a gravitational field because electrons have mass and mass produces gravitational field, but it's not going to be a circular gravitational field. An electromagnetic field, how do you know D is not the answer? We don't know what an electromagnetic field is, right? We will actually in our next unit. It still won't be the answer, but next unit at least it would be an option for you. This unit, it's not even an option for you because you haven't learned about it yet. The answer is B. Good? Ready for a quiz on Monday?
Yeah.
Quiz number 15. Do I have it on up there? Oh, I do, yeah. Yeah, there you go.